into some content. So I'm not going to talk too much today, but there's a couple things I want to point out, and we're actually going to do a few examples together. Let's talk about arc length first. So what we talked about last time was these vector valued functions, right? We called R of t a position vector. That's basically made up of 3 parametric equations, right? We use these to make things like our helix. So we also found the velocity was the derivative, which is basically, remember, the derivative of your position vector or your initial vector is your tangent vector. And the instantaneous speed is the magnitude of the velocity. And then if we were to take the velocity vector and divide it by the speed, we get the unit tangent vector. All right, so that was all stuff we discussed last time. All right, so let's talk about arc length. Not a difficult concept. This is basically the speed, and the idea of arc length in 2 dimensions is the same in 3. Basically, what we're doing is we're getting the distance traveled by integrating the speed. This is the exact same formula you would have used in Calc 2 with parametric equations. So to find the arc length, all you do is set up the magnitude of the speed, the magnitude of your velocity or your derivative, which is this part right here. And then you integrate from A to B. Now, obviously, depending on how messy our magnitude comes out, that integral might be very nice or very difficult. But let's say we're asked to find the total distance on a take-home problem. Set it up by hand and let Symbolab or Wolfram Alpha do the calculation for you and include your screenshot. Okay. I'm not going to give you a nasty one to do by hand on the in-class part of the exam. So this is perfect spot to utilize technology in doing the integrals. And that's basically arc length. Any questions about that? We're going to try one today too, so you'll get to practice it. Again, if you can set it up, after that, it's just single variable calculus. You're just doing an integral. Now, what ends up happening is, as you can imagine, because of the radical, a lot of them are going to be not very easily solvable without like a trig sub or something like that, which is why, like, if it gets nasty, we're just going to go right to technology. All right, so arc length's not a new concept. It's something we've talked about before. Curvature probably is. You might have talked about curvature a little bit with conics. Here's something that probably seems pretty straightforward. The curvature of a line, a straight line, is 0, right? No curve. Now, this curvature of a circle is constant, because what the curvature is basically looking at is how something bends. You know, how harsh is the turn? The sharper the turn, the more the tangent vectors must change direction. All right, so just to kind of give a comparison of, if we had a turn that looked like this versus a turn that looked like this, we're going to have a larger curvature on the inside one, because the acceleration vector has to do more work to turn that tangent vector versus out here, which is much slower, gradual turn on our tangent vector. So basically, what curvature is doing is measuring how curvy is a curve, right? Right away, let's think about where that could be interesting. Think about tires, right? Going on a racetrack. Well, depending on the curvature, you need to know what speed the tires can handle in order to stay on the track. So that's basically what we're looking at with curvature is, okay, how steep of a curve is it? And then we can throw that curvature into our calculations to say, okay, this is how fast you can go around this turn without going off the track. Or spinning out or flying. Yeah, exactly. So the other nice thing is you notice the inverse relationship with the radius. So that's the way that the curvature is basically measured.
So the bigger the radius, the smaller the curvature.
Yes, and let's think about why that is. Now we already said this point has I'm glad you asked it, has a bigger curvature than this point, right? We can all agree on that. You know, we can imagine going around, this is going to give us a lot more pull than this one. Well, think about this. If we were to draw a circle that included that point, I'll do this as best I can. This circle would look like something like this, right? But this circle might look something like this. So we see how the bigger the curvature, the smaller the radius, because it takes a smaller circle to represent that piece of the curve. The sharper the turn, the smaller the circle we'd have to put on that turn. Which is, you know, again, it's cool because it's intuitive, right? Now we can kind of make sense of what the curvature is. So what's going on with the curvature? Basically, it is how the tangent line, the tangent vector is changing with respect to distance. Okay, so we're almost looking, it's almost like we're looking at an angular velocity. It's not quite the same thing because we're not going through angles, but what we're looking at is how quickly is the tangent line changing with respect to distance or the arc length. So basically, this is how we find K. And like I said, as a reminder from last time, the tangent vector is the derivative of our position vector. So the unit tangent vector is just the unit vector of the derivative of our position vector. Okay. So again, just kind of reminding us from last time, you know, we were calling R of t our position vector. Then the tangent vector would be r prime of t, which is also v of t. It's also our velocity vector. It becomes a unit tangent vector. So unit tangent vector if we divide by the magnitude. Now, remember why we do that. That preserves direction and gets rid of magnitude, because all we care about is how quickly this thing is changing direction as we go along the arc length. We don't want its magnitude in the calculation. That's why this uses the unit tangent vector. Now, I'm going to show you a couple forms that make this a little bit easier to deal with. So don't worry about this formula right here. There's going to be two that we're primarily going to use. So we're going to use chain rule to break this apart. All right, so we're looking at the derivative of our unit tangent vector. So that's the change in tangent vector with respect to the change in time, divided by the change in arc length with respect to the change in time. Well, that's this. All right, so again, t is a unit tangent vector, not just a tangent vector. But all we have to do is take t prime of t, the magnitude of that, divided by the magnitude of r prime. Now, this isn't always going to be work or be our most useful form. Okay. This is where this comes from. You know, we know that arc length is the integral of the magnitude of the derivative, or r prime. So basically, what we're looking at is the second fundamental theorem of calculus, which is the derivative of the integral gets us right back to the derivative. Now, so this is just what I'm showing you here is just how all this stuff is related. So you don't think it just pulled it out of thin air. All right. Now we do have an alternative formula. This is going to be one of the ones we're going to look at today. In fact, one of the problems you guys are going to work from the worksheet, you're going to do both forms and make sure you get the same answer. Because sometimes the first one is better. Here is our alternative notation. This is probably the one you saw in the video. Depending on what we have, this one won't always work. This is easy, but it really depends on R prime coming out constant. If it doesn't, what we find is this one is going to be easier to use in a more general sense. I'm not, because it takes a lot of time, I'm not going to go through the equivalence of the two, but if you want to see it in the textbook attached to this course in 12.3, in the at the end of the chapter, it shows the equivalence between these two forms mathematically, how they work. So feel free to check that out if you're wondering, hey, where the heck did that come from? Okay, now we're going to take that second formula and leverage a bit of technology. We're going to do a problem together. So K equals magnitude of R prime of T crossed with R double prime of T all over magnitude of R prime of T cubed. Okay. I just had to put that up there because we only have one screen today and I want to bring up the problem we're going to do so everybody can see it. Okay, so the problem we're going to do is from the worksheet. Let's do that. All right, we're going to do number 3. You guys are going to do 1 and 2. All right, what we're going to do is we're going to do a little bit by hand, a little bit by technology. So I want you to kind of see how this plays out and how the interplay between it. All right, can you guys see that one okay? Actually, why don't I do this? Here is the worksheet, so that if you guys don't mind passing these around, that way you have it right in front of you. Okay, so begin with, there's really nothing crazy going on. So we have R of T, and it's got these 3 polynomials. What do we got? 3t cubed minus 9t squared minus 6t plus 7.
7t cubed and 5t cubed minus 9t squared plus 3t minus 7.
Thank you. Okay. I almost lost all my board space on that one. Guys, the first couple steps are as straightforward as taking the derivative, which is good because that gives me another thing that I wanted to remind you of. I know I've talked to the folks in here, but we'll make sure I say it to everybody. Next week, we are going into partial derivatives and we're going to really be moving with derivatives. So if you need help with practice with your derivative rules, make sure that you start to work on those again. You might want to use your whatever derivative rule sheet that you used back in Calc 1. While you get those back in your head, bring it for class on Tuesday, because we need to we're going to start taking lots of derivatives starting next week. Okay. So the nice thing is these derivatives aren't bad at all. So what do we got? 9t squared minus 18t minus 6. 15 is going to go away. And then we got 18t minus, oh, that's a negative 17. I'm trying to read my own writing. Minus 21t squared. 15t squared minus 18t plus 3. And there's our R prime of T. And we also need our R double prime of T. And so we've got 18t minus 18 18 minus 42t, 30t minus 18, right? So again, it's just a matter of taking derivatives. Okay, well now we start to get into the formula. We see that we have a cross product on top and then we have a cubed on bottom. Now, by hand, as you can imagine, this is going to be a mess, right? So what we're going to do is we'll calculate these values with the t value already plugged in. Okay. So that is something that we can do in Wolfram Alpha. And let's just see what that would look like. So what you can do, and this is kind of a nice thing, I'm going to put them in, but again, I'm going to put them in with we're just going to do 0.2, not both of them. So 9 times 0.2 is 18 times 0.2 minus 6. Okay, there's our first component.
0.2 times 0.2 minus 21 times 0.2 squared.
1
And
times
then comma 15.
Squared, comma
15 times 0.2 squared, and then minus 18 times 0.2.
15 squared minus 18. Thank you for your help. I appreciate it.
And then plus 3.
Plus 3. All right, so there's our first vector.
And the double one is 18 times 0.2 minus 18, comma 18 minus 42 times 0.2. And then the third is 30 times 0.2 minus 18.
Okay. So hopefully you guys were watching me. Did that look like it went in okay?
Yes.
All right, let's see what we get. Okay.
Numbers.
Yep. Well, let's do this.
So let's go ahead and take the magnitude of the.
Yep. Oh, I didn't like that. Shouldn't be 0. Okay.
What I do sometimes is I'll just pull open another tab.
Yeah, let's try that. Oops. All right, so we'll use a second one. Negative 33.12, comma, negative 0.88, comma, negative 48.96. All right, so we get for our formula that the numerator is 125.652. Now, one of the things, that we always want to make sure of, we always want to check accuracy. So actually, we could, okay, looks like we're good. Make sure that we're not rounding off and losing any of our accuracy. All right, so that gives us our cross product. The other thing we need is r prime of t, the magnitude of that cubed, which I'm going to take right from here. Whoa. All right. Let's do one more window.
Sometimes I just get like 40 tabs.
Absolutely.
Right now.
All right, square root of 14. So we got 125.652 divided by square root of 14 cubed. And I don't think that's the right answer. Let's see.
So we get like, I got the same thing, 2.39, at least on my calculator.
Yeah,
So I know that it's at least calculated.
yeah, we calculated that part correctly. Something else went wrong.
I mean, it's a lot of numbers to input originally.
Yeah, oh yeah, it happens, right? Yep, lots of room for error. Let's see. 18 times 15.
The concept makes sense.
0.2 squared, 15. 0.2 squared minus 18 times 0.2 plus 3 crossed with 18 times 0.2. We won't spend a lot of time on this. I can double check it later. 18 minus 0.2 times 0.2. 30 times 0.2. Make sure I put in the magnitude right. Here we go. Here's my vector.
Didn't paste in.
Let's try one more time because for some reason I'm not seeing the vector. This might.
Isn't what you're putting in right now the?
Yeah, what you're putting in is the cross between R prime and R
Yes.
double prime.
Oh, yeah, that's
So you
right.
need to just do
Over here is what I was. I see what you're. Yep. Okay. Let's do it here. It's okay.
R prime times double.
Came out the same. All right.
So what we do is we do R prime times 0.2. So you can just copy that in and calculate where it is, and then we can cube it, right?
Mm-hmm. Which was r prime times 0.2.
Yeah.
Let's try this again. It's a different result, isn't it?
Yes. So that's
Yeah,
6.4.
9.643.
I get 0.140.
That's what we should get.
Yep.
Yeah.
That's the right answer.
Yeah.
Not sure what happened that first round.
Oh, yeah. Yeah. This is its 2 pi over root 5 is the other form.
So, okay. So we got that working. I'm not sure where the error was, but that's okay. Getting back to the take-home problems, if we had to justify our answer, we could use something like the snipping tool. And what I would do is, again, get what you input and what the output was.
If the input tracks off like really far, kind of like in this one.
Well, see how it has the interpretation below? So I can still see that
okay.
part. And also, you know, like knowing what the output is, this will be plenty.
Okay.
And so what I would do for my submission, I would take this image, and because I did 3 different ones, I would take that image, this image, and this image, and I would just post that as my work underneath the derivatives.
Okay.
Does that make sense? You put them in like a Word doc as an image, and then eventually save it as a PDF when you're all done and ready to submit. Now, as far as that work, the work that I did on the board, a couple options there. You know, you could use an equation editor in Microsoft to type it in, or if you handwritten it on like a whiteboard or a piece of paper, you can take a photo of that and put that in there into the Word document as well. Okay. So that was part of the reason I wanted to do this one with you guys. Sorry about the mistake, but I just want to give a chance to see how you can use technology and still justify your answers. And it is literally just using screenshots of what you put in and what you got out. Wolfram Alpha, Symbolab, any other program that you end up using. If you do stuff in your graphing calculator, take a picture of your input and output on your graphing calculator. Okay. It's not enough to say graphing calculator. I need to see the work or the justification. Let's call it that. Okay. All right. So that's how the formula is used. And guys, like I said, these calculating curvature is a mess. I'm actually not going to put curvature on the in-class part of the exam. It's going to be, I'll tell you right now, it's going to be a take-home problem. You're going to get it in like an hour. So now you know how to do it. You can do exactly what we just did and be done with that problem. Just don't do it wrong like I did. Take your time on it. Okay, that's what I wanted to talk about in 12.3. So if there's no questions there, then let's go on to 12.4. Close some of this stuff down. Apparently, I not have it open. Thought I had it.
I have one question.
Give me 1 second. Sorry, it was open. No, it is not.
Oh, I think I know what happened.
On that input.
Yeah, so
What-
if you didn't paste in the thing and it just did magnitude of vector, it'll kind of like try and do a lesson and it gives you the automatic
Yep.
input of 3, 2.
I had noticed that.
1.
Yeah, I noticed that vector said vector input 3, 2, 1, and I kind of ignored it at first, but after seeing that our magnitude was radical 14, which is 9 plus 4 plus wait, 3, 2, 1. That would have been right,
9 and 4 is 13 and then 1 is.
which is where the rad 14 came from. Yeah.
Because it was a 3D vector instead of 2D, so.
All right. So let's move it open. Almost there. Luckily, this is not a long section. But we will do a few problems from the worksheet. All right, so cylindrical and spherical coordinates. These we're getting introduced to now, but are going to be a bigger deal, especially when we get into integration, second half of the semester.
Professor, can you hear me?
Yeah.
Hey, so I had a question. I did try to get your attention earlier, but I don't think you heard me. Sorry to kind of cut you off in 12.4. But you know, in the 12.3 questions, it was saying solve at when t is equal to this and when t is equal to that. So is that just saying that we use that k formula evaluated at t at that value and t at the other value, and that's it? Simple as that?
Correct. We did it for 0.2. We would
Okay.
redo the same steps for 0.5.
Okay, and everything you put into Wolfram Alpha was the equation at that t value. You you didn't leave it as T variables. The screen was very blurry. The screen recording that we got is very blurry today. I don't know why. So I really couldn't see the details of what you were putting into Wolfram. But it just looked like you put in 0.2 for all the values.
Yes, I put in 0.2 for the T's and just left everything else as the equations, just because I didn't want to take the time to solve them. But
Okay.
we could have calculated those at 0.2.
Okay, cool. That was my question. Thank you.
And as far as the screen issue, I don't know if anybody else is having that issue. I'm not sure what's going on there. It could have been, well, no, the screen should have showed up fine. Okay.
So if you, like for anyone who attends live online, if you do side-by-side speaker view, then you can control the dimensions of the shared screen and the video camera recording. So you should be looking at the shared screen because that comes in clear, whereas the camera recording doesn't if you're viewing from home.
Oh, side by side speaker. So we should just keep it in side by side speaker most of the time, unless he's doing stuff on the whiteboard, then I assume standard.
Yep.
Okay, cool.
All right. Thank you, Professor Tar. Okay. Let's talk about these coordinate systems. So far, we've talked about everything in terms of rectangular. We may find situations that it's easier to use coordinate systems that are different. You know, if you remember polar from your Calc 2 or your pre-calc experience, that's a perfect example. So, you know, if your curve is symmetric with the origin, kind of like a circle, then something like polar becomes much easier to use. So rectangular coordinates require the horizontal and vertical distance from the origin. Polar require the distance, the direct distance from the origin and the angle between that distance and the positive x-axis. So just a reminder of what polar looks like. You know, this would be a point in xy, but it's also a point in r comma theta. And for some reason, I'm not able to annotate on these. I don't know why. Okay. So
I think if you go back and enable editing on the entire PowerPoint, then it'll be a lot edited.
oh, I missed the enabled editing. Good point. Okay. So all that's really going on here, thank you very much, is basically yeah, there it is. This is all just right angle trig. This side is x, this side is y. And that's where this relationship comes from. Just our Pythagorean relationship. And tangent is opposite over adjacent, or y over x. So this is this is basically polar. And what we need to be able to do, one of the things we're going to do today is go back and forth between the two systems. So for instance, if we want the rectangular coordinates, it's very straightforward. Basically, all we have to do is plug in r. So polar always goes r comma theta. So we would plug in 5 for r, pi over 6 for theta, into x and y. And we've got the xy coordinate. Now, where we got to start to think a little bit more is going is going the opposite direction, So what if we had the polar coordinates given by -4, 5? Okay. And there's just one thing I want to make sure I point out, and that's why we're going to do this one. R is easy. R is the square root of -4 squared plus 5 squared. So we've got 16 and 25, so rad 41. So there's our R. We also need the theta that goes with it. So we know that according to this, tangent theta equals y over x. So -5/4. Which means we've got to use the inverse trig function. So this is going to be an arctan. So, sorry for writing all over the screen here, but I want to show you something. We put in -5/4. Anybody mind calculating that for me? You can do, what'd you get?
Oh, then radians are in degrees.
Let's do both.
I have both. So,
Okay, let's start with radians.
radians is -0.896. Oh, yada yada yada.
Okay,
And then degrees is -51.340. Oh, yada yada yada.
51.34, so on and so forth. Okay.
Yeah.
All right. Now, something very important we need to talk about here. And this is something from your trig that I need to make sure I remind you about. Now, first off, a lot of times we'll want theta in between 0 and 2 pi. Neither of those angles are between 0 and 2 pi or 0 and 360. In fact, what quadrant do those angles lie in? The fourth quadrant. What quadrant does the point -4, 5 lie in?
So it would be this one.
It lies in the second quadrant, right? So two issues with these angles. One is they're not, let's talk radians. We'll mostly use radians in here, degrees occasionally, but mostly. And unless you're told degrees, it's automatically radians. So we know that this angle here is actually in the fourth quadrant, but we should be in the second quadrant. Well, what this gives us is our reference angle. So, oops, make a little more space. So what that reference angle is the angle between the horizontal and our line. So we know that our point, let's use different colors so you guys can see this. Maybe, there we go. We know that our, we're at -4, 5, we're over here somewhere. Yeah. Let's try that again. There we go. We're over here somewhere. So the reference angle is the angle between our line and the horizontal. So what I know about that angle right there is that it is 0.896 plus some decimal points radians. That's still not our angle because we want to give this angle. Well, if that's 0.96, we know if we kept going, it'd be pi. So this angle is pi minus 0.896. So on and so forth. So in radians, our point would be rad 41 pi minus 0.896, yada, yada, yada. The reason I wanted to go through that with you guys is because we can't just take what inverse tangent gives us depending on what you put in. You know what, if you're in the first quadrant, it's probably not going to be a big deal. But outside of that, you got to make sure that your angle is in the same quadrant as your point. Okay. Another thing that I'll point out now, because we'll talk about it a little bit in the other coordinate systems. The other thing that you can do is if you make your radius negative, then the angle is actually 180 degrees or pi the opposite. So now we could either use the negative 0.0896, so on and so forth, or if we wanted to be between 0 and 2 pi, it'd be 2 pi minus 0.896. So there, because we can keep going around this circle, there's an infinite amount of ways we can define a point in polar, any single point, because we can always go another 2 pi around the circle and get back to the same point. We always keep it as simple as possible. I mean, this would be the one that we would use. We'll talk a little bit about that idea of a negative radius down the road. Questions about that? All right. So, like I said, I want to spend some time on that because I know it's something that you probably haven't seen in a while and definitely worth bringing up. All right, so these are, these are plots that are easier to do in polar than rectangular. Now, a circle isn't too bad. This could be x squared plus y squared equals 25, but in polar, it's r equals 5. When it really gets tricky is over here on this side. If we had to integrate the area between these two, this would be a nightmare to do in rectangular because we would have to break it up into separate integrals. But in polar, all we're doing is going from r equals 4 to r equals 6.
Is that how you would like write it, or you find like the polar equation and subtract 1 from it?
These are the polar equations.
You just end with R equals 2.
And no. So if we wanted the area between these, well, we haven't done
Okay,
polar.
we're
And
talking about the area.
yeah, we're not quite to polar integrals yet, so I don't want to go too far down that road. But these would be the limits of our polar integral.
Okay.
So think of them as think of limits of integration, right? To get area. We could do either or for this circle, but when you have like this washer, it's much easier to do in polar because the equations for it are so simple. So just a little bit of motivation for why we need polar. Not moving enough. Thank you. So what happens now is we're going to extend into 3D by just adding the z-axis. So it's polar in the xy plane. We add in the z-axis, we get what are called cylindrical coordinates. So things like a cylinder and a cone, well, hence the name cylindrical coordinates, are going to be easier to do in polar. So basically what cylindrical coordinates look like, you can see we have polar in the xy plane, but then z is just some vertical distance above. So we still have, that same thing going on in the xy plane. Yeah. Basically the same equations as before. So it's all those polar equations, tangent of theta equals y over x, extended into 3D by just adding up a z coordinate. And that's the same z coordinate from our rectangular. So then what we want to talk about are what are called fundamental surfaces. So we want to think about, now we're thinking in 3D. If we set r to be a constant, so if we had the polar equation that r equals 2, what surface would we get in 3D? And think about what we'd get in the xy plane. We'd get a cylinder. Because we get the circle in the xy plane, then adding in the z is going to make it go up and down. This one's kind of a tricky one the first time you see it. What do we get if we set theta to be a constant? All right, so now theta is going to be our constant. So here's theta. Theta is not allowed to move. It's set as a constant. What kind of?
Would it just be a plane?
Tell me more about that. It would be a plane. Tell me more about that plane.
The plane would be at an angle of theta to the x-axis.
Yes.
It'd be.
How would it be compared to the xy plane? And you can kind of see it in that picture. What I want you to, imagine There's our, that would be kind of like what our plane would look
So
like.
it would
Like
be
a-
normal to it,
It'd be what?
normal to it.
Yep, it'd be normal or perpendicular to the XY plane. And it would go through the Z axis. Very nice. That's a tough one to imagine. This last one, what if Z is a constant?
Then it's a plane parallel to the,
Plane parallel to the XY plane, same as in rectangular. So here's the three examples. These things are called fundamental surfaces. The reason we care about these fundamental surfaces, and we will revisit these in a couple modules, is because anytime we're dealing with surfaces that are of the shape or a combination of these shapes, we want to be in cylindrical coordinates because they're easier to plot. So if we see a cone, if we see a cylinder in our figure, or we see a plane that's perpendicular to the XY plane that goes through the Z axis, we know we want to be in cylindrical. Again, kind of foreshadowing where we're going to go later this semester, so I don't want you to worry about that too much right now, but I just want you to get used to this idea. We will go through those exact 2 slides again later this semester, and I'll ask you the same questions. Spherical, last coordinate system, and then we'll start doing some stuff. Spherical is an interesting one. It depends on rho, phi, and theta. All right, so what rho is the distance from the origin, and it's just the direct distance from the origin. Notice how R had to lie in the R has to lie in the XY plane. Phi does, rho does not. So this thing that looks like a P is called rho, RHO. So that thing can go literally anywhere, and it is just the distance from the origin out to our point. Phi is the angle between rho and the positive Z axis. And then theta is the same theta from polar. That's the exact same theta we were just looking at. All these relationships, nothing you have to memorize, right? Because you'll have a note card for the exams, are all just right angle trig. All right. So the reason X is R sine phi cosine theta, well, excuse me, rho sine phi cosine theta. Well, what's rho sine phi going to give us? Rho sine phi gives us the opposite side, which is over here. And then cosine theta from before. So basically, what's happening is this part here is taking the place of R from polar. Yeah, Mark.
The symbol in front of our cosine, is that the same symbol as B? Because they look different.
This is rho, this is phi, and this is theta.
What's the one that right in front of our cosine?
That one's.
Oh, that's phi. It's one's an uppercase, one's a lowercase. You're right. They do look different.
Okay, cool.
Yeah, those should match. Those should match. One's an uppercase phi, one's a lowercase phi.
Phi theta.
Mhm.
I smell angles.
Yeah, this-
That's not right.
This should be the same as this guy here. Good call. So basically that that rho sine phi is taking the place of R from our polar equations. And rho cosine phi takes the place of our Z. Again, it's just all right angle trig. Rho squared is x squared plus y squared plus z squared. That's basically from our distance formula in 3D.
So rho is just the magnitude of a vector? No, well, rho is the distance formula applied to a 3D point, right? A point in
Yes.
3D.
Rho comes from the distance formula of a 3D point.
Okay,
It's specifically the distance from the origin out to our point.
gotcha. Okay. Cool.
Okay, so you're gonna have all the formulas. It's just gonna be a matter of knowing how to use them. And just like last time, we have our 3 fundamental surfaces we'll look at. So first off, if rho is a constant, Remember, rho is the distance from the origin. So if we set the distance from the origin to be a constant, what kind of surface do we get? We get a sphere, hence the name spherical coordinates. All right, theta constant, we already know that one because it's the same theta as before. It'll do that same plane that's perpendicular to the XY plane, goes through the z-axis. Now, what if phi is a constant? Let's look at phi again. Phi is this angle right here. That's a constant. And then theta is going to spin this thing around. What kind of shape are we going to get? We're going to get a cone. Yep, with its point at the origin. So those are our fundamental surfaces for spherical. And again, we will use these more later. Right now, what we're doing is just kind of looking at going back and forth. Okay. I'm going to do just a couple problems from the worksheet. I'm not going to take a lot of time on these because I do want you guys to have time to do at least a couple problems. And I've already taken longer than I meant to. I just want to do a couple of from 12.4 of converting formulas just because it's not always obvious the first time you see it. All right, so we'll just do a couple of conversions. We won't do a lot of them. Okay, here's the here's the 12.4 if you guys want to pass it over around. Let's talk about 3A. So 3A. We're given the polar equation R equals 5 cosine theta. This is something that can be graphed in Desmos in your graphing calculator. You just need to change your mode to polar. So if you want to convert this, at first it's hard to see how, but what we can do is multiply both sides by an R. So this becomes R squared equals 5R cosine theta. Now the transformations, the substitutions are much more obvious. R squared is equal to X squared plus Y squared because we're going to rectangular. R cosine theta is X, so that equals 5X. Now,
Would you want us to simplify that, or?
we need to simplify it because right now all we know is that this is a circle. But where is the circle centered and what's its radius?
So move 5 to the other side.
Yep.
And do complete square. or whatever.
You got it. X squared minus 5X
25, right?
plus something, you're close, you're very close.
Or wait, no, that's.
Y squared
double-
equals 0 plus something.
That's double 5, so that's like.
Yeah, so what I like to do, I like to go to the next line, and I know that what goes right here is exactly half of this.
So that's.
So what goes here is negative 5/2 squared, and then we got to keep our balance. Plus y squared equals 25 over 4. Now we know we have a circle centered at 5/2 comma 0 with a radius of 5/2, because remember, this is the radius squared. So, you know, I know you probably haven't had a lot of practice at completing the square. That's why we're doing this one together. You're not gonna have to do we're not gonna be exchanging formulas back and forth a whole lot. Again, it's just to get you familiar with these other coordinate systems. Let's see, I think I want to do just one. How are we doing on time? Let's do one more. That'll still give us a half hour. We'll do one more and do a habit on there. We're going to do 8C. So Z equals 2x squared plus y squared. And we have to convert this over to spherical. All right, now it would have been nice if it was plus 2z². It would have made things really easy. Unfortunately, we don't have that. So we're just going to use the transformations. So z equals rho cosine of phi. Guys, I don't even have these memorized. So like I said, do not try and memorize these transformations to spherical. This is the perfect thing for like the note cards. 2, and so x is rho sine phi cosine theta squared 2, and y is rho sine phi sine theta squared. So what's going to happen? You know, we're going to have 2 rho squared sine squared phi cosine squared theta plus 2 rho squared sine squared theta, excuse me, sine squared phi sine squared theta. So we've got a cosine squared sine squared, right? This is going to happen a lot. It's going to help us simplify. So we're going to pull out the 2 rho squared sine squared phi out of both of those. And we get left with a cosine squared theta. You got it, plus sine squared theta.
Which is just 1.
That's our Pythagorean identity. Now this is equal to rho cosine of phi.
So we're gonna have like. cancel.
And what we like to do is solve for rho. Okay, just like in polar, whenever we can, we like to solve for r, or in rectangular, whenever we can, we like to solve for z. Now, it's not always going to be possible, but in this time it is, because what we can do is divide by 2 rho sine squared phi on both sides. And I'm only doing 1 row because they'll cancel out on this. So that gets rid of this, and this. That'll get rid of those. And now this is fine for a final answer, but I just want to show you where the answer on the back came from. And that is from taking this and saying, okay, well, that's 1/2 cosine phi over,
Cotan, secant, yeah. no,
yep,
just-
sine phi, and 1 over sine phi.
Okay.
And so that's where I'm going to write on this side just because I don't want to go any lower. 1/2, that's our cotangent phi. And then there's our cosecant phi. Again, this would have been fine for a final answer. Sometimes we like to write them without fractions whenever possible, hence the reciprocal trig identities.
We normally like to keep the non-reciprocal identities, then, or does it matter?
It doesn't matter. There's a bit of personal preference there. You know, this is a cleaner final answer, so a lot of times you'll see this, but you know, we're so used to dealing with sine and cosine. I mean, there's nothing wrong with leaving it in this form.
Can you explain the last line? I don't understand what happened in the last line, the 1/2.
Oh,
So right here, we divided by 2, so there's the 1/2.
Okay, cool.
Cosine phi over one of the sines, and then
Okay.
1 over the other sine, because it was sine squared on the bottom.
because they're being.
Oh, okay.
And then we just used our trig identities that cotangent phi is cosine over sine, and cosecant is 1 over sine.
Sine over phi.
Yeah. Other questions about this one? Okay. We do have some time left. Let's work on a few problems.